So I hope to share with you a little bit about what we call the VBT projects, or the vinyl benzothiamine project. And this is the active research that's going on in the Gurley lab, which is a collaboration between me, Professor Gurney, and also Professor Lee. Now, VBT, or vinyl benzothiamine, is a pretty complicated molecule, and right now, looking at it, you probably don't understand what those symbols mean. But what I want to do is give you a broad overview right now and show you why we're doing this project, and give you a little bit of background about what you'll be doing over this semester in Chem 114, as well as in 225. So we've decided to integrate this research into the curriculum, one, to help our research lab, but most primarily to teach you the real methods of research and how to do research independently in the laboratory. So why are we making this molecule? Well, it turns out that we're interested in preventing the spread of infection. So basically, to sum it up, there are two different kinds of bacteria, really. There's some good bacteria and bad bacteria, and most of the bacteria that's in hospitals is actually pretty bad. And more people die actually in infections that are received in hospitals than actually for what they're getting treated for in the first place. So MRSA is one example, and in 2003, 64% of hospital bacterial infections were this MRSA infection. And greater and greater needs for antibacterial agents are needed to prevent this sort of spread of infection. So let's begin. How do you prevent bacteria from surviving or thriving on surfaces? Well, there's one quick way in organic chemistry that we can prevent these bacteria from surviving, and that involves what are called quats, or quaternary ammonium compounds. You see here this nitrogen has 4 groups attached to it. It's positively charged. That is a functional group we would call a quaternary ammonium, or a quat for short. It turns out that quats disrupt the cell bacterial wall. So here you can see it basically disrupts it, and cytoplasm is able to leak out. And that's one way that we could prevent bacteria. This acts as a quat would act as a bacteriostat, not a bactericide. So we don't have to worry about antibiotic resistance, because it actually acts upon each individual cell. And bacteria can't become resistant to bacteriostats. So how could we put this quat on a surface which then would yield it a bad surface for bacteria to grow on? How do we render surfaces bacteria-free? Well, one idea would be to make an antibacterial coating. In this case, we're going to call it a polymer, which is really another word for plastic. And immobilize it on a surface. We have two different functions here. One, it has to be antibacterial, and two, we have to be able to immobilize it. Let's first focus on that antibacterial part. We already know that quats, or quaternary ammonium compounds, are one of a few functional groups that prove to be antimicrobial. And so if we could put this quat on a coating and then coat surface with it, that surface then could be antibacterial in nature. So we could create a polymer which we can use to coat surfaces that has this group, a pendant group, like attached to it, like a hand and arm that has a quaternary ammonium group, have it in the structure, and then you can see here's one method we could do that. We could take a polymer, which just means poly means many, mer is a unit. So here in this case I show you this is styrene and this is polystyrene, in that a polymer of styrene. Styrene itself is the monomer, mono 1 mer unit, 1 monomer of styrene. We run a reaction and we can make a polymer, and so this represents the structure of a polystyrene or many styrene polymer. One way to make this antibacterial would be to change the monomer, this unit, to have a quat on it. For example, we could take this starting material, which we then could put a quat functional group on, and then make the polymer out of this new monomer that has this quaternary group. So in this case, now we have a polystyrene polymer that has these pendant quaternary ammonium groups. And so you can see we would have an antibacterial polymer. The only problem is, because of the high charge, these positive charges, we'll learn it's just like sodium chloride in that it's water soluble. So it is an antibacterial polymer, but unfortunately it washes off with water. Now, all these structures don't make a whole lot of sense, but let me show you a simpler way to look at this using my favorite things, Legos. We'll take a moment to look at the same idea. Well, you can think about this first monomer right here. This is called vinyl benzyl chloride, or VBC. That could just be this little guy here, like that has linkages groups on this side, as well as a group here. This reaction, what we're doing is actually taking the quat ammonium group, which is this little guy here, and then we're simply linking them together. In chemistry, all we're doing is forming a bond between this guy and this guy, so it's equivalent, the first reaction, in just linking them together to make this. And in any reaction, you do it once, you do it twice, you do it 3 times, you can do it 4 times, you can do it a mole of times, depending on how many starting materials you have. So there, I just made 4 of those individual, what we're going to call VBA units. I can run the next reaction here, which is the linking of those units, and this is the polymerization reaction. And that simply will take these individual units like this, link them together, so that's 2 together is now a dimer. We can put a third one next to it, maybe this way. Click, that's a trimer. Let's put another unit here. We'll put this one like that. That's a tetramer. And let's put this one like this, doesn't matter. Now we have a pentamer. And so the polymer, this is now a pentamer, and if we continued going, we would eventually get longer and longer and have a polymer. Let's now go back to our slide. Well, we were able to get to this polymer, and the problem was that it washes off. So that wouldn't stick to any surfaces and would fall off pretty readily. So how do we now immobilize? How do we make it stick to a surface? Well, it turns out that if we cross-link polymers and increase their molecular weight, the larger the molecular weight of the polymer, the harder it is to solubilize. We'll talk about solubilization in class soon. But how do we put it on the surface if it's insoluble, right? We can't transfer it to a surface if it starts out insoluble. So we want to have a soluble polymer, a fluid polymer to put on the surface, and then have a way to cross-link it to make it a really big polymer. Here's a schematic. You could take a fluid polymer, like so, and then find a way to rigidify it by lengthening the chains or making it a rigid polymer. And so, again, here you have a unit where when you do a reaction, it can cross-link or form a network polymer on the surface. And so it would be also really nice if we could reverse that, so you could put the polymer on the surface or you could take it off. And this is chemistry that was developed by John Warner at the Warner-Babcock Foundation. Well, we can steal an idea on how to do this process from DNA. DNA, when light shines on it, there's a group called thymine that actually dimerizes because of light. When light shines on DNA, for example, here you can see sunlight coming in. These 2 yellow thymine units in the backbone of DNA can actually dimerize or link together. And this is the photoreversible damage that can occur with DNA on your skin when you're standing out in the sun too long. So here's a schematic representation of what the thymine dimer would look like. So if we were able to put this same group, this thymine group, this guy right here, into the polymer backbone, maybe we could shine light on that polymer and then be able to increase the or cross-linking ability and make it stick to the surface and not be reversible. So how do we put a thymine group onto a polymer backbone such as polystyrene? Well, again, we're going to try to do this exact work. Here's another representation of the thymine, the thymine being dimerized with light and on. You can see that there. And so there's the thymine groups. Shine light, you make that link, and that explains a little bit more about that graphic. This is exactly what another reaction that we can do in order to put the thymine unit on the polymer backbone in order to make this new monomer. Okay, there's those groups, just to show you some more schemes. So here's the reaction that you're going to start doing in Chem 114 this semester. Again, we're going to start with the vinyl benzyl chloride monomer, add to it the thymine, make vinyl benzyl thymine so that you can make a polymer of the vinyl benzyl thymine, or PVBT in this case. Okay? So what are you going to basically be doing this semester could be represented quickly by this schematic here. Once again, we